Hi, everybody. Welcome to the MISRA Parallelism Safety Critical Guidelines for C++ 11, 17, and hopefully 20 and 23. My name is Michael Wong. With me, people have worked on this work for quite some time. I have Andreas Weiss from Woven Planet, which is an autonomous vehicle company. He's a staff engineer there. I have Ilya Birilov from Intel. He's a principal engineer who's been contributing a long time into functional safety and the MISRA standard. And then I'm a distinguished engineer from CodePlay. All of us have been on the C++ standard committee for a long time. So just basic acknowledgements and disclaimers. And after that, what we're going to talk about today is about the current status of C++ safety using both MISRA and C++ core guidelines, based on our work of adding parallel safety rules, which is going to be the second part that Ilya is going to show you some of the examples that we found. And then the third part, I think it really brings home why these safety rules are needed. And Andreas is going to talk about a specific automotive safety case for especially the kind of autonomous vehicles that's going to be on the road. So I think that's something very interesting to look at. So first, why do we need it? Well, there's definitely been a safety API revolution happening in the industry with a massive proliferation of committees and groups following safety security concerns. And this is partly driven by the large number of robotics and autonomous vehicles that is coming online. And in response, we're going all in on safety critical ethics, functional safety, AI, ML safety. And some of the things that we're working on, C++, SICL, obviously something I'm interested deeply, wants to take those and be employed in those sectors, but they have to be made safe, okay? And this is actually driven probably by the topmost initiative called the United Nations Economic Commissions for Europe, the UNECE WP29. And out of that, that's driven all these other groups to add all these safety things like RISC-V, like the Safety Critical Club from the UK, ISO 26262, 21448, MISRA, SAE, and SC42, and supporting all these devices up there. So there are many standards, and most of these standards, and I've kind of pretty much collected all the ones, most of the, probably 99% that I know. Maybe I missed a few, I don't know, maybe not, but these are the written rules they're usually written as a set of rules for the most part that are widely accepted good programming practices. Now, they usually have a specific audience in mind, and they also may be automated checkable rules or a set of human checking rules, good guidelines. And the thing that I find that is discriminating between them is that there are so many safety standards, but they all have something missing. And that's why this group kind of came together. Now, there are the ones that are safe, but not modern, like C++ that doesn't support 11, 14, 17, or 20. This is JSF++ and MISRA, okay? They are also the ones that are C++ 11, 14, 17, and 20 specific, but they're not necessarily safe, okay? Because they might be coding guidelines, or they might have not, and in some of these cases, they haven't followed the standards once their work was done. So the original MISRA C++ document, for instance, completely disallowed dynamic memory and did not cover standard libraries and security, But the new one is going to address some of these. The new the Autosar document defines how to use dynamic memory, exceptions, templates, inheritance, and virtual functions. But they've kind of stopped their work and transferred their work into MISRA. And that's why we're kind of hoping that MISRA takes us a little bit further forward. But we also don't want to forget core guidelines. So let's compare the standards, okay? So the Autosar guidelines was introduced because Autosar could find no appropriate coding standards for the use of modern C++. And at that time, it was 11 and 14 in critical and safety-related software. So that they can support their new adaptive Autosar platform, which supports parallel for highly connected and autonomous vehicles. Now, the standard most commonly used within automotive and other industry is actually MISRA C++. Almost everything else is based on it just because it was the very first. Okay, so it may not be the best, but it was there from the very beginning. So MISRA C++ 2008 is designed for and explicitly mandates the use of C++ 03, pretty old, and are directly adapted from MISRA C++ 2008. And there are several other coding standards and resources that are referenced or form the basis of Autosar rules. And these are the JSF rules, the high integrity C++ rules, the CERT rules, and the C++ core guideline rules, okay? And here you see which version of the standard these maps to, okay? We're pretty much now, having seen all these rules, we now know which are the most important remaining ones that we should follow. Not to say the other ones are irrelevant, because they don't adapt to the latest standard. You know, they have to be used depending on where they ratify to. So the Autosar guidelines contains a section that says traceability to existing standards. And this basically details how each rule in the MISRA, high integrity C++, JSF, C++ core guidelines, and CERT coding standard relates to the Autosar rules. And it categorizes the rules as identical, small differences, significant differences, or rejected. And this shows that 91% of the MISRA C++ 2008 rules have been at least partially absorbed into Autosar. 54% of C++ core guideline has been absorbed into Autosar. And the MISRA C++ and core guideline are now, the ones in red, are basically the most important remaining set of rules because they're actively maintained. And so we're going to only look deeply at these two to lead us to a future of safe, parallel, concurrency, heterogeneous guidelines. So the core guidelines, Biana already gave a great talk on type and resource safety on C++. You should go to that talk, which was yesterday, but you could go to it on YouTube, I'm sure. And Biana says, you know, you can write C++ programs that are statically type safe and have no resource leaks. You can do that without loss of performance and without limiting C++ expressive power. I do believe in that. He further says, this supports the general thesis that garbage collections is neither necessary nor sufficient for quality software. Our core C++ guidelines make such code simpler to write than older style C++, and the safety can be validated by tools that should soon be available. And they are available in like GSL and CLion. But the quote kind of tells us that it is C++ core guideline is aiming for bug-free code with high performance, the intersection with elegant coding style. And that's a very important area to support. MISRA, however, now being probably the most popular coding standard that is pretty much used across the board from automotive to embedded to medical, has its progeny in MISRA C, and there was some progeny with, and MISRA kind of relate to the motor industry, but nowadays they disavow that and say it's pretty much for all embedded systems and need safety, or any systems that need safety. And the difference, our group thinks, is that they will always, we acknowledge that code will always have bugs, but they must do no harm. This is the Hippocratic oath that we're trying to put on top of coding standards. All right, so having seen all these things that are happening, what is still missing? There's still a lot. Despite all this progress, all this is still safety APIs for sequential programming. There are only a few rules for parallel and concurrent programming and none for heterogeneous programming. And that too is changing because we've been working on this parallel working group within MISRA C++ to look at coding, to look at adding safety coverage guidance for parallel and concurrent programming. It just happened to be the most handy group around. We could have probably done it in C++ as well. So our intention here is to build safety of heterogeneous on top of that as well. And this is because there's always going to be a possibility of dirty data, faulty hardware, integrity problems. And you need freedom from interference, which is much harder to do in a multi-threaded system. And if you're going to take it to AI and ML like autonomous vehicles intends to, their safety will almost definitely require some sort of heterogeneous devices, as they already do, even without the safety, because most mapping programs and intelligent vision programs are basically offloaded. So the end result, hopefully we can now transfer these to C++ or to my language, SECL, okay, in order to make them safe and secure. So This is our phase one spreadsheet collecting all the parallel concurrency heterogeneous rules that we have, building on the graph from the ground up. We gave this talk in 2020 on a few of the rules, and we always have the intention of aiming our coding towards our findings toward either the core guideline or MISRA, okay, maybe both or neither, depending on what the rule says. So some history, stage one, we did extensive deep analysis of 81 rules, started in 2019 at a MISRA meeting where we asked, actually I think it was Ilya who asked, why are there no rules for parallelism in MISRA? So through 2019 to 2021, we completed phase one by culling from all these standards that I mentioned before, about 81 rules. Some of them actually just had no parallel rules at all. Many joined, we averaged 5 to 8 per meeting, and consulted outside concurrency and safety experts as well too. There's a shared drive of phase one analysis. And then after the analysis, we summarize all the status here as to what is accepted to core guideline or MISRA, and what is rejected and what is deferred. We also separated into decidability. Is it hard or easy for a machine or human to see a violation? And this turned out to be very important, so let's talk about it. So let's talk about decidability. This is how easy it is to detect a violation, either by human eye examination, a coding review, or machine interpretation of coding patterns. It's always hard to know the intention of code, especially in some dynamic context or something that requires whole program analysis. And we find that in general, human reviews are generally simple rules, code snippets, or basic syntax that matches the intention. Automated tool, however, can examine millions of lines of code very quickly, issue a report, and usually they can find really good things that have static scope. They can be convoluted, but it's still doable if the syntax is pretty clear and it's pretty local. And that's the truth. That's the case with this generation of tool. However, in dynamic scope, it's much more complex. And we're basically issuing a call to tools to build these kinds of decidability for automated tooling, because this is still hard even for today's generation. And it probably requires some kind of whole program in analysis. And that's because the intention is hidden, especially in dynamic scopes, where you have to go across multiple compilation units. There's also rules that are probably good for both human and automated tools, but those are generally simple cases and the intention is pretty clear from the syntax. And there are rules that are good for neither. They're just simply so complex, even for machine, to figure out if there's a violation. In that case, pretty much humans have almost no chance, especially if you're examining millions of lines of code. This is the case where intention is not clear. And in that case, we're calling for an attribute called intention that might be able to tell you what the intention is doing. Like, I'm actually trying to do a double check locking pattern here, okay? Now, this is not, I have seen other authors trying to issue a feature that's kind of like that. And so we're not actually breaking any particular new ground, but this would be something that we need. And honestly, within these consortium, they're also thinking of looking at attributes that tells you what these code was supposed to do. All right, so where should parallel, concurrency, and heterogeneous rules go? Well, we kind of separated into 4 quadrants, obviously, between human decidable or tool decidable. Okay, and then what's the preference? If it's easy for human to see the code violation and easy for a tool, then it should really pretty much go to C++ core guideline. And obviously, MISRA tools can do that too. If it's easy for the human, but it's hard for the tool, it's definitely for the core guideline. And on the tool side, it might be a meta rule or some undecidable rule or directive, you know, because there's going to be lots of false positives, and it might be just too terrible for tools to be able to handle, at least for this generation, without some intention tag. If it's hard for human, easy for tool decidable, then that's the primary audience is probably some sort of tool, some sort of static tooling that can examine this code. And it might, but on the core guideline, it can still go there. It could be a meta rule or a directive. If it's hard for both human or tools to decide, then it's going to might go to neither, because it might be a meta directive or coding guideline. You probably definitely need something like an intention attribute to tell us what are you trying to do there. So when we collated all the rules, this is the data that we got. We always separate it into categories, and categories are important in MISRA because it tells you whether a rule can be issued, I guess, excuses for the violation. Okay, and mandatory means that there's no way of working around it. You have to follow the rule. Require means that there's a few cases you can explain why you might want to break the rule. And advisory means there are a fair number of cases that would allow you to violate the rule, and you would have to explain, why that is and things like that. Take it to a safety engineer, and they would get approved. And directive rules are rules that are generally not machine checkable. So we found about 8 mandatory, 12 required, 12 advisory, and 5 directive. Out of these, 27 were easily decidable by humans. 1 that was medium, 20 was complex, and 9 we haven't decided yet. Out of the ones that are for the automated tools, we found that 20 were decidable on a local level, probably on a compilation unit. 6 was decidable if you could see whole program analysis. And 7, maybe, these were so hard that they may be decidable on a system analysis. You have to see the spreadsheet. And 8 we just don't think anybody could tell whether there's an exact violation. And there's about 11 that we still have to process. So out of this, we chose there were 24 that we accepted for entry. For the initial phase, and 12 of these should probably aim either at both core guideline and the tools. 5 of these should probably aim for tools and the core guidelines because they're hard for the core guidelines to pick up, but they still could be added to the core guidelines. There were 4 that could be modifies existing core guideline, and 3 were exactly the same as the core guideline. And 26 was deferred for the future. 18 was rejected. And with that, I'm going to get ready to transfer over to Ilya on section 2 on parallel safety rules. Thank you.
Okay. So let us dive deeper into several rules and see how it matches the categorization which Michael showed recently. Let us start from the rule 13. Mutexes locked with std lock and try lock shall be wrapped with RII-friendly adapters within the same scope. The main intention of the rule is to employ RII for controlling the state of the mutexes in exceptional conditions, even if you need to lock several mutexes at once. Looking at this rule, you can see that it is generally detectable via review because you can almost always find out what is the type of the object which is going to std lock, unless you are trying to use auto too much, but it is typically not the case for this function. It is also easy to detect by tool because tool is trying to compile your code and it always knows the type of the object, especially when it knows exactly the line of code where everything is applied. It doesn't need to look deeper into in your code base for that. And with that, it is very friendly either for review, for human, or for tools. Thus, this rule looks like a good one for both C++ coding guidelines and MISRA. If we are looking at the C++ core guidelines right now, we will find 2 rules which are near this one, but do not exactly match. The one on the left is use RII and Nova plain lock unlock. And on the right, use std lock or scope lock to acquire several mutexes. If you try to apply them both at once, you will avoid the use case which was described by this rule 13. Because if you are not trying to wrap the mutex which is going into std lock by something, you will need to use unlock, which is disabled by the first rule. But this specific use case is not exactly amplified on this C++ core guidelines set. Thus, some tuning can be applied to CP 21. Okay, let us look into example of another rule. Use std call once to ensure a function is called exactly once, rather than double checking locking pattern. The intention of the rule is to avoid common issues which can be incorporated into the code if you try to reproduce the common concurrency algorithms. And it is reasonably detectable by review because you can always try to ask the code writer what his intention was when he was writing this code. And if it was double checking locking pattern, you say him, hey, there is a call once function. But for the tool, it is the different story. It is a relatively reasonable task to find the double checked locking pattern, but it is a difficult task to find the pattern which is wrong when you added some errors in this double checked locking pattern. So with that, there is no, we are not sure that tools can find all the cases in this specific rule. With that, it seems very applicable for C++ coding guidelines. And we still believe that it can find its place in MISRA because at least some patterns which are close to double-checked locking, but it's not exactly the same or exactly the same, can be found by tools. And thus, it is better for C++ code guidelines, but still applicable for MISRA. If you will try to look at C++ code guidelines, you will find exactly this rule. Do not write your own double-checking locking for initialization, because other things can be used within the existing C++ 11 standard. So with that, on C++ code guidelines, the work is done, and we still have some work to do it in MISRA. Another example. The order of nested locks unlocks shall form a directed acyclic graph. This is a very complex rule which is intended to avoid deadlocks via improper using of synchronization primitives. It is very hard to detect via review because it typically spread around different pieces of code and you will never see it in one place. Or almost never. At the same time, it is also not very simple for tools. Tools should see those synchronization primitives not only in the source code you're currently trying to compile, but also in the other pieces of code as well. At the same time, if a tool sees only a portion of your code, it still can try to detect violation of direct acyclic graph in this piece of code. So some automation is possible. With that, we see that it is hard to apply for C++ code guidelines as a rule, but it is much better for using in tools and thus applicable for MISRA. In case of human-only rules, we can refer to the rule 8, verify resource management assumption of std thread within the implementation of standard library of your choice. It is the rule which is hardly applicable for code review or by detecting via tools, because it targets the higher level. It targets the documentation of your system and standard library, and probably operating system as well. With that, we don't see it is right fit to C++ core guidelines. And there, it is not fitting the tools or static code analysis tools. At the same time as a directive rule, it can be applied for MISRA, because we are trying to direct a user, not the user, we direct an integrator or reviewer to go and look at the documentation of your dependencies, which a generally very important thing in trying to build a safe software system. With that, we see the rules for main 4 buckets, the rules which are mostly applicable for both tools and human review, the rule which is more applicable for human or for the tool, and the rule, this one, which is not really applicable for either code or tool review. And now we can switch to a use case from Andreas.
Thank you, Ilya. Now that we've seen some of the rules, how they look like, and what the tool might diagnose, I want to talk a little bit about the other side. So what a developer that needs to follow these rules, what their point of view on this whole thing is. And the first thing that you might ask yourself if you're working on safety critical software is, why do I need concurrency guideline at all? So the one obvious answer to point out here is, of course, that if you're following the ISO 26262, which is the ISO standard that specifies how to write safety critical software for automotive, it lists concurrency aspects as one of the topics that need to be covered by modeling and coding guidelines. But of course, that is not a very exciting answer, and it kind of misses the point. Because, like, why would you actually want to have concurrency in a safety critical system, right? Like, should a safety critical system actually contain such kind of code when we all more or less know the dangers of it and how hard it is to get those systems correctly? And if you look at typical embedded systems that you find in automotive software today, then you will see that especially the ones that have safety requirements addressed to them are typically very static in nature, and they, in particular, they follow only very static execution patterns. Now, automotive hardware faces the same problems as desktop hardware in that it stopped getting faster a while ago. So there also you now have multi-core chips, simply because that is the only way that you can increase compute power. But the way that those chips are programmed is typically that you partition your entire software stack into distinct parts, and then have just like one part run on the one core, another part run on the other core, and they never have to interact, right? So you keep them completely distinct already by design, and the stuff runs in parallel, but since there's no interaction, you don't have to worry about any of the concurrency issues, right? But this is about to change. So as I said, like these traditional automotive systems, it's all very statically scheduled. So typically the way that this looks like is that you have a number of tasks in your system that you want to run. And each of these tasks is given a predetermined time slice. And the scheduler just invokes one task after the other. And usually all of these tasks run to completion. So whatever they set out to do, they just do all of it in one go. And then it's the next task's turn. The only case where you can even get preempted in your task is if you miss like a real-time deadline or something, but you're not supposed to do that. Like that would already be a fault in a system that runs as it's supposed to be. This never happens. All the tasks just run. So the complete schedule for such a system is configured upfront. You basically write down what the order is in which tasks get executed. And then the actual execution at runtime is more or less completely deterministic. In particular, tasks not scheduled to run in parallel will not overlap. So even if you have multiple cores and multiple tasks running there, you can schedule them in a way that there are no concurrency issues. The actual synchronization between the cores, because I mean, if you go to the lowest level, just above the hardware, you still need to worry about some kind of synchronization there. This is handled by a very thin basic software module layer, which is does basically all the kind of work that an operating system would do on a desktop machine. But this is very primitive. This is not really comparable to what you would find on a desktop operating system. So in general, the component interaction across cores is minimized. Tasks typically don't have to worry about concurrency. The problem with this is, like, this works very well if you have only a small number of components, or if the interaction between components is minimal. As soon as the interaction between components increases, it becomes harder and harder to actually find such a static scheduling that is suitable for running them. And then if the number of components increases as well, then this eventually becomes a really difficult problem. What's worse is that with the highly compute-intensive applications that we see now, in particular with in the context of highly automated driving, you actually need parallel computation to process the data in time. It's no longer enough to have all of the tasks run in parallel on their own single core, simply because the amount of data that you have to process is so large that you actually need to have like true multi-core computation, that like you're working on the same sets of data in parallel, and maybe even go to heterogeneous computing. So in particular, if you're talking about autonomous driving, you probably cannot do this on a CPU alone. You probably will need some kind of accelerator running in the background. And on such a system, avoiding concurrency gets really, really difficult. So we kind of have these two worlds here. And like if you're still in the old world, then you might not actually get into contact with concurrency at all. And this set of rules that we're working about there might not concern you very much. But if you're already living in the new world where you're working like with these powerful multi-core CPUs, parallel computation, potentially also using auxiliary hardware accelerators, usually those also have a fully fledged operating system running at the bottom. There will be lots of concurrency, and having asynchronous APIs is very likely going to be the default in such a system. So to illustrate this, I'm going to show a short example from adaptive Autosar. So adaptive Autosar, for those of you who don't know, is a standard for writing automotive software. It defines like certain interfaces, like how an application should look like, how it should behave, how to communicate with others, and so on. So what we have here is taken actually straight from the Autosar documentation for communication. And what we're trying to do is like simply read some sensor value from a radar sensor. So the first thing that we're going to do in Autosar is we're going to run a service discovery that will actually find the service that it provides this sensor data. And the way that this works is we're going to call such a start find service method. which will run asynchronously. So the method will just return immediately, and eventually it will invoke a callback when the service became available that gets passed as a parameter of the handles to the services. And then eventually we will have to stop the find service, but here in between lots of other things could happen. So what we will do then inside the callback, whenever a service is found and the callback gets invoked, we check like if actually any handles were found, and if such, I just take the first handle that I find to instantiate a service from that. And now this service provides this field update rate, which is the interface to the sensor that I'm interested in. So I get this field and I call .get on it to get the actual sensor value. But what happens here is we have another asynchronous step. We don't get the sensor value immediately. Instead, I'm going to get a future to the sensor value. So here I either have to call future.get, or what adaptive Autosar actually prefers is that I use .then to chain my asynchronous computing steps. So this works the same as the .then from the concurrency TS for C++. So these APIs were designed in 2016 mostly. So that's why they used this approach for from the concurrency TS, because that was the thing to do at the time. C++ by now has other ideas. In particular, if you have been attending some of the talks talking about the executor concepts, then like these ideas have evolved in C++ a little bit over the years. But in Autosar, it's still basically like in the concurrency TS. The .then gets passed to lambda. The lambda will get invoked whenever the value from the future becomes available. So when I call .get here on the future, that gets passed in as a parameter. This is guaranteed not to block, but it will give me right back my sensor value that I was interested in. So these are all these steps that I need to go to get to this one sensor value. There are alternative APIs which are more synchronous, more blocking, but if you're in a large complex application, it's very likely that you will want to access it like this through the asynchronous APIs. And you can see there's lots of potential for concurrent execution. So if you're living in such a world and you still need to be, you still have safety critical requirements, then you might want to use these guidelines. So let's look now at an example. Like let's say when I read my sensor value down here, I actually want to share it with the outside world, right? So typically what happens there is that I get the sensor value, I do some kind of processing on it, and then this processed result I want to share. And this processed result, since it was computed by my application, it's not available through COM in the beginning. And if I don't want to put it on the COM interface again, then I can just share it by having a shared struct and just writing it into there. So this shouldn't be too fancy. I just capture a reference to this shared object and then just write to that inside the lambda. So now if I do this and other people are accessing the shared data as well, it's likely that I do have to synchronize, right? So I add a mutex to the struct that synchronizes access to the data. And I'm going to lock the mutex down here, right? Because like this might be the first time that I'm actually using multi-threaded programming, and like this seems the right solution to me. So now if I apply a rule checker, it will probably complain because we have a rule that says do not destroy objects of type mutex if the object is in a locked state. Because I only lock it, but I never unlock it. And I'm going to say, oops, that was probably a mistake. So I'm going to fix that by add an unlock call. But there is another issue. So the call to get might actually throw You might remember a future can either hold the expected result or it can also hold an exception if the result could not be provided. And then if it holds an exception when calling get, the exception will resurface and it would just propagate right out of the lambda, skipping my unlock call. And I would have the same problem as before. Which is why there's another warning that would advise me to not call member functions of student mutex directly. If you're familiar with how MISRA rules work, you will already know this. But if not, you might be wondering, like, why do we get like 2 warnings for what is basically the same problem, right? Because if I don't call the lock member function but use the lock guard instead, then also the other problem that we saw in the beginning cannot happen. And this is very typical. Like MISRA rules are often redundant, and this is by design. In particular, we expect users in some cases to deviate certain rules. Like, for example, here you could say, well, I have been guarding all of my execution path with explicit try-catch statements. So I know that it's actually fine with using the lock-unlock, and I have a good reason for using it. Then you can use that as an argument to deviate from the rule, and it would allow you to do that. But if it then can still find an execution path where you actually forgot the unlock, you will get the other warning. So you have like these multiple layers of warnings that you can run into. So okay, we're going to solve that by adding a scope lock. Like if you actually look at the rule, this is the suggested solution that it will point you towards. So you don't have to guess here. And now hopefully everything is fine. No, actually there's one more warning. Because we actually forgot to give our lock a name. So we'll get the warning objects of type scope lock shall always be named. Otherwise the object will be constructed and immediately get destroyed, and we didn't actually obtain the lock. So we fixed that as well. And with that, our code is warning free and should work. So does this now mean that concurrency is fine for safety critical software? That if I'm warning free, then I know that I will be bug free, and this is of course not the case. Like as you've seen, these rules are rather simple. It's like if you're familiar with multi-threaded programming, you probably know all of these advice already. You probably would have written the correct code to begin with. So the rules really only attempt to catch the common errors. They're not magical. It's really like trying to enforce the common wisdom. And it's important to realize that there will only ever be one building block in a larger safety strategy, right? So if you're building a concurrent system, there's lots of aspects that you have to consider that need to be carefully evaluated and that need to be thought about as part of such a larger safety strategy. And these rules, they're just one building block. They can increase your confidence. They can, in particular, they can ensure you that you didn't make any like stupid mistakes, but they cannot guarantee bug freedom. And with that, it's time for some final words from Michael.
Okay, sorry, I'm just trying to bring myself back up. And okay, great, thank you. Thank you, Andreas and Ilya. That's really great examples. So basically, we're going to need to adapt even more concurrency items to safety. And now this is a chart of parallel concurrency features entering C++ 11, 14, 17, and 20, separated into asynchronous parallel agents, parallel collections, multiple shared states, and heterogeneous distributed sections. It is showing how we build on increasingly higher abstractions, starting with base components. Now, C++ 20 is shown in red. We have things like JThreads, we have interrupt tokens, and coroutines for asynchronous agents. And for parallel collection, you know that C++ 20 offer additional back execution policies, algorithms like unseek. Mutable shared states, we have a lot, including atomic ref, atomic share putter, lattice barriers, semaphores, and many memory model fixes. And we're going to have to adapt to all these and support all these. So where are we with all these in our parallel rule guidelines that we've been building? Well, we're not actually inventing new rules. We're basically just documenting common wisdom. And that takes time. It takes time for people in the industry to use it, and us to interpret it and try to figure out what is it safe, and how, is it at what level of safety? Is it decidable? So MISRA next is really mostly going to be MISRA 2008 reinterpreted to modern C++, plus what Autosar has contributed. And definitely we need more manpower to be able to do that. They've actually have increased from when I first joined, when there were just 4 people, now to almost 15 to 20 people contributing to this. But we also need more experience on the safety of new features. And so as a result, I would surmise, I'm not making any official statements, that MISRA next will not really cover C++20 and might even miss a few C++17 features. Now, our work, MISRA Parallel, will also be in stages. So obviously we've covered things like atomics, async, memory model, shared lock, some parallel algorithms and futures, but we still need more deep dives on things like unseek, policies. And of course, we are still looking forward to contributions for C++20, 23, and 26 features that are coming. So what's our plan? Well, in 2021, our plan is to integrate our work with MISRA 22202X, the next release. We are seeing 17 rules that can go to MISRA C++ next, 17 rules that can go to core guideline, 4 core guideline rules that would need to be modified, and then the rest would have to be deferred to the next release. We would reset at that point and then start going through our monthly working group meeting to go through the deferred rules. And these are going to become increasingly harder. Onward from 2022, well, we're going to work on those deferred rules. We're going to add new rules covering things like coroutines, parallel algorithms, and executors if they come along. And we're going to aim to release MISRA C++ next, okay? So basically, this is ongoing work that won't stop. But C++ is going to need to also work well with ongoing external safety initiatives that add safety layers to concurrency. And then also ML AI safety, because they obviously must use heterogeneous devices for the most part. So from sequential to concurrency using automotive as a use case, just like what Andreas has done, we note that 26262 was primarily sequential, and only adaptive Autosar was able to switch to adding parallel and concurrency. Then from concurrency to heterogeneous, you're going to need to adapt things like ML, AI, trustworthiness, bias, fairness, and safety. And those are very difficult and often non-quantifiable verification, validation things that you have to do. Some of that is now downloaded into the next version of 2626262 called 21448 SOTIF, which stands for Safety of the Intended Functionality. There are also other concurrent groups, parallel industry action like UL 4600 and SAE's on-road autonomous driving group that is dealing with that. So in summary, we believe we're going to make some useful contributions to either core guidelines, to MISRA, to both, or maybe neither. And that the idea is that it's on this shared drive if you want to get it. And then ultimately, we're aiming so that the industry, to satisfy what we think is an industry need to support safety API revolutions. With that, I'd like to thank you. Thank you to my friends and speakers and to our hosts. Thank you to you, to the audience, for listening to us, and give you a call. This is a call to action to help us if you have expertise in this area. Thank you. We'll probably start taking questions now. I think the host will start reading out any questions that you have.
Okay, I think we have one question. Does MISRA or C++ CG prefer using semaphores over condition variables?
Let me try to answer. Semaphores are part of C++20. As Michael said just recently, we are not covering much from C++20 yet on MISRA side. So no, we just don't dive into the part yet. And I don't think there is a similar rule on C++ core guidelines either.
Yeah, so with regards to the C++20 feature, I think it's also important to reiterate something that that Michael said in the talk. We try not to invent new rules. We try to just document common wisdom, so to speak. And with newer features, that is increasingly difficult. Like with semaphores, you could argue that like semaphores as a synchronization primitive have been around for some time. But in particular, if it comes to like the specific pitfalls of the API that is being used in the standard library, we don't have a lot of experience with that. And as a result, it just can take some time before we actually find any good rules that we could write down. And then this is just the nature of the process. It's a bit unfortunate because it makes it harder for people to argue to use the newer features soon in such software. But that's just how it is.
Okay, thank you for the answer. Well, any more questions? Okay, I think we have 3 more questions in the Q&A panel.
Yeah. There's one question. How would you try to convince a team used to MISRA C to switch to C++? I think that's a question that we think about a lot also on the MISRA working group. So like C has still a big place in embedded development, right? And usually C developers are reluctant to switch over to C++ because C is a much simpler language. It's in many regards easier to use. The biggest argument in terms of safety is probably the increased guarantees that you can get from the type system in C++. There's some very compelling examples for that. For example, if you look at the talks from Dan Sachs, he likes to give a lot of examples here how C++ can lead to fewer bugs, particularly in embedded software. But in the end, it's difficult to convince someone, right? Because if they're happy with C and they don't want to learn C++, then the benefits would have to be pretty significant for them to switch. So you can try to convince them by showing them examples like these kinds of bugs could have been caught by the type system. I don't think you can do much more than that, and then just hope that they see the reason. And if they don't, then maybe they have good reasons for not switching. I mean, that might also happen. Yeah, do you want to take one of the other questions?
Okay. I almost typed it in the Q&A, but let us cover it more verbose. Could I compare MISRA to SPICE? These are standards targeting different parts. SPICE is mostly targeting the process of development, and MISRA is targeting the specific rules which are there applicable for specific language. So they both can be used simultaneously in one project and should be used simultaneously in one project because they are actually targeting different parts of the development. One is the process related, another one is related to the specific code you're writing.
Okay, then I see we have one last question, and I'm just going to grab that, if it's okay. What are the most harmful mistakes you noticed in your work, besides not unlocking the meetings? So actually, the harmful mistakes are not the ones that keep me awake at night. Because the harmful mistakes that I noticed, those are the ones that get fixed, right? The big question and sort of the fundamental question in safety critical software is actually about the mistakes you did not notice, right? The mistakes that go into production without you knowing. So of course, safety critical software is like any other software. You make the same kinds of mistakes there, you get the same kinds of bugs, you run into undefined behavior, you debug stuff, you fix stuff, and you hope that at the end of the day you found everything, right? The crucial difference is that safety acknowledges the reality that you can never find all of the bugs, and tries to account for that by ensuring that if you have bugs left in your program, at least the effect of the bug will not cause a human to be harmed in the end, right? That is sort of the overarching idea of safety, right? Even if things go wrong, they should never go so wrong that somebody gets hurt, right? This is also like sort of what a lot of these guidelines try to drive you toward. They try to advertise like coding styles, coding patterns that are less likely to be harmful, right? And if you combine that with the full safety strategies where you have like different levels of fallback that try to catch even unforeseen errors, then you can get to a pretty high confidence that you didn't overlook anything. But yes, like for the mistakes that I noticed, like all of the bad stuff that you also see in other kind of software, right? Like we're no, when we write software, we're no different than any other person. We just make the same kind of mistakes.